the described scenario with pole light supply from a 50 amps rated branch circuit using number 6 copper wire, then reducing to number 10 copper wire at the pole handhole with a 30 amps fuse, does not comply with the National Electrical Code. Firstly, NEC section 215.2 A1 states that branch circuit shall have an ampacity not less than the maximum load to be served. The branch circuit is rated for 50 amps, but the number 10 copper wire installed from the pole handhold to the ballast has an ampacity of only 30 amps, violating NEC section 215.2 A1. Secondly, NEC section 240.4 D addresses conductor ampacity for multiple circuits. It states that where a conductor is used for more than one circuit, its ampacity shall not be less than the sum of the currents to be carried. Here, the number 10 copper wire is used to carry the current for the 50 amps branch circuit, although a 30 amps fuse is installed. This is still a violation of NEC section 240.4 D because the conductor must be sized to handle the potential current of the branch circuit. Finally, NEC section 240.13 states that overcurrent protection for conductors shall not exceed the ampacity of the conductor. The 30 amps fuse is installed in a branch circuit rated for 50 amps. Although the fuse itself is rated appropriately for the number 10 copper wire, the overall circuit design violates the NEC because the branch circuit overcurrent protection exceeds the ampacity of the downstream conductor. In summary, the number 10 copper wire must be upgraded to size appropriate for the 50 amps branch circuit, while the branch circuit overcurrent protection must be reduced to match the ampacity of the number 10 copper wire. A 30 amps fuse does not rectify the situation of undersized conductors on a 50 amps circuit. This ensures compliance with the NEC and maintains electrical safety. Remember to always consult the latest edition of the National Electrical Code and local amendments for specific requirements in your jurisdiction. Proper conductor sizing and overcurrent protection are crucial for preventing overheating, fires, and other electrical hazards. The installation described violates multiple sections of the NEC concerning conductor ampacity and overcurrent protection. To reiterate, NEC section 215.2 A1 mandates that branch circuits have an ampacity no less than the maximum load served. The scenario violates this because the number 10 copper wire, with its low ampacity, is part of a 50 amps branch circuit. NEC section 240.4 D further reinforces this principle by requiring conductors used for multiple circuits to have an ampacity at least equal to the sum of the currents they carry. Even with the 30 amps fuse, the number 10 copper wire is still considered part of the 50 amps branch circuit, leading to a violation. Furthermore, NEC section 240.13 emphasizes that overcurrent protection should not exceed the conductor's ampacity. Although the 30 amps fuse protects the number 10 copper wire, the entire branch circuit is protected at 50 amps, creating an imbalance. The correct approach involves either upgrading the conductor size throughout the circuit or reducing the branch circuit overcurrent protection to match the smallest conductor's ampacity. Understanding ampacity is critical. Ampacity refers to the current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Several factors influence a conductor's ampacity, including its material, size, insulation type, and installation environment. Copper and aluminum are the most common conductor materials, with copper generally having a higher ampacity for a given size. Larger conductors have a greater cross-sectional area, allowing them to carry more current without overheating. Different insulation types have varying temperature ratings, which affect the conductor's ampacity. Conductors installed in free air typically have a higher ampacity than those installed in conduits or raceways due to better heat dissipation. NEC Table 310.16 provides ampacity ratings for various conductor types and sizes under specific conditions. It is essential to consult this table when determining the appropriate conductor size for a given application. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect conductors from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined value, preventing overheating and potential fires. The rating of the overcurrent protection device should be matched to the ampacity of the conductor it protects. Installing an overcurrent protection device with a higher rating than the conductor's ampacity can lead to conductor damage and increase the risk of fire. NEC Section 240 provides detailed requirements for overcurrent protection, including the selection and installation of fuses and circuit breakers. Branch circuits are the portion of an electrical system that extends from the final overcurrent protection device to the outlets or equipment served. Branch circuits can be classified based on their voltage and amperage ratings. Common branch circuit ratings include 15 amps, 20 amps, 30 amps, and 50 amps. The type and size of conductors used in a branch circuit must be appropriate for its rating. NEC Article 210 provides requirements for branch circuits, including the number and type of outlets permitted on each circuit. The scenario described highlights the importance of proper electrical design and installation. It is crucial to select conductors and overcurrent protection devices that are appropriately sized for the load and comply with the NEC. Failure to do so can create hazardous conditions and increase the risk of electrical fires. Always consult with a qualified electrician or electrical engineer when designing or installing electrical systems. In this specific case, the reduction in conductor size from number 6 copper to number 10 copper at the pole hand hole creates a weak point in the circuit. The number 6 copper wire is capable of carrying 50 amps, while the number 10 copper wire is only rated for 30 amps. This means that the number 10 copper wire is being subjected to a current that exceeds its ampacity, which can cause it to overheat and potentially fail. The 30 amps fuse installed at the point of attachment of the number 10 copper wire is intended to protect it from overloads and short circuits. However, it does not address the fundamental problem of the undersized conductor. Even if the fuse trips, the number 10 copper wire may have already been damaged by the excessive current. To correct the situation, there are two possible solutions. Firstly, the number 10 copper wire could be replaced with a larger conductor that is rated for 50 amps. This would ensure that the entire circuit is capable of carrying the full load without overheating. Secondly, the branch circuit overcurrent protection could be reduced to 30 amps. This would protect the number 10 copper wire from overloads, but it would also limit the amount of power that could be supplied to the pole lights. In either case, it is essential to ensure that the wiring complies with all applicable codes and standards. Ignoring these regulations can lead to dangerous and costly consequences. Always consult with a qualified electrician to ensure the safety and reliability of your electrical system. Furthermore, it is important to consider the specific application when selecting conductors and overcurrent protection devices. For example, if the pole lights are subject to frequent surges or overloads, it may be necessary to use conductors with a higher ampacity rating or overcurrent protection devices with a faster response time. Regular inspection and maintenance of electrical systems are also crucial for preventing problems. This includes checking for loose connections, damaged insulation, and corroded components. Addressing these issues promptly can help to prevent more serious problems from developing. In conclusion, the scenario described does not comply with the NEC because it violates multiple sections related to conductor ampacity and overcurrent protection. The correct approach involves either upgrading the conductor size or reducing the branch circuit overcurrent protection to match the smallest conductor's ampacity. Proper electrical design, installation, and maintenance are essential for ensuring the safety and reliability of electrical systems. Remember to consult the latest edition of the NEC and local amendments for specific requirements in your jurisdiction. It's also worth mentioning that the type of load connected to the branch circuit should also be considered. If the pole lights draw a continuous load for 3 IOs or more, the branch circuit is considered a continuous load. In such cases, NEC Section 210.19 8.1 requires the branch circuit to have an ampacity not less than 125% of the continuous load. This means that a 50 amps branch circuit supplying a continuous load should be loaded to no more than 40 amps. The overcurrent protection device is also required to be rated to not less than 125% of the continuous load, as per NEC Section 210.20. These requirements further emphasize the importance of proper conductor sizing and overcurrent protection for branch circuits. In summary, when evaluating the compliance of an electrical installation with NEC, it is essential to consider all applicable sections and factors, including conductor ampacity, overcurrent protection, load type, and installation environment. Consulting with a qualified electrician or electrical engineer is always recommended to ensure that the installation meets all requirements and is safe and reliable. Also, consider voltage drop. While the code does not explicitly prevent voltage drop, it is a great idea to plan. Voltage drop can cause lights to be dimmer at the end of a circuit. Number 6 wire is suitable for shorter distances, depending on the load of the lights. The length of run from the power source to the furthest light and the total amperage draw of all the lights on the circuit would be needed to calculate if there is an acceptable voltage drop on the circuit. In addition, always check with local and state guidelines in addition to the NEC.